Hello everyone, so let's look at to this problem 8.30 page 418, and for this question we are given case of cylindrical. So if you can read from the questions, we have two different regions. The first one defined from area or region phi from 0 to pi. So the first one here belongs to our first region, which has a value of mu1 given as 2 mu naught, and then the other region defined from pi to pi, and this one belongs to the second region, which has a value of mu2 given as 5 mu naught. Okay guys, so we're also given the B2 vector, the magnetic field density, the B2 vector given as 10R component plus 15 phi component minus 20 Z component in millitesla. Okay guys, so if you can look at to these expressions, we know that when we see the R and Z appear at the same times, so but we should know that this is a case of cylindrical, right? Because there's no theta and there is Z and R appear at the same times, so this is case of cylindrical. And then now we are going to find the B1 vector, right? The B1 vector which composed of B1 normal plus B1 tangential, isn't it? Okay guys, so based on this structure we can simply note that at this interface, right, or at this boundary, so the vector component actually will go in that directions or in that directions. All right, so we can simply say that since the an normal vector here going in that direction, so by right actually this an is belong to the phi component. Right guys, so we can simply know that this component actually is belong to the B2 normal component. Alright, so if you can see from these expressions, the B2 here has 15 in phi, so by right this phi component will go in positive phi direction, and it has 15 millitesla value. So from here we can say that the B2n here actually will go in these directions, right? The B2n, because this is your second region B2, and then this is phi directions, and since positive, so the B2n will go in these directions, right? And then we can simply say that for the B2 tangential actually belongs to the rest of the components, whereby it has this 10R minus 20Z. So now we have B2T equal to 10R minus 20Z component millitesla. Okay guys, so this is our first step. We need to define ourselves, so which one is normal component and which one is tangential component. It depends on structure. Alright, so now we are going to find the B1 as mentioned here earlier. So B1 here guys is composed of two main components, normal and tangential. So if I want to find the normal one, we can simply use the normal component equations of magnetic case, whereby we have this one B1 and is equal to the B2n, or we can simply state that B1n is equal to this 15 phi component, milli-Tesla. Right, guys? And now we're going to find the remaining component, which is our B1T. So the B1T can be obtained using the second magnetic boundary condition equations, whereby it can be expressed as here, H1T minus H2T is equal to the JS. Okay, guys, this JS is our surface current density that maybe appear on the interface, but since there's no mentioning in the equation that there is surface current, so we can simply assume that the JS in this case is equal to 0, whereby at this interface or boundary along this interface, the JS is assumed to be 0. Okay, guys, or we can simply have these final equations, which is H1T is equal to the H2T. So let's convert this H term into B term by simply applying this formula. The H1T is equal to B1T is over mu1, and H2T is equal to the B2T over mu2. And we do have the B2T already, as mentioned earlier. So now I'm going to find the B1T is our target. So bring this one up there. So now equal to mu1 over mu2 B2T. So let's substitute the value of mu1 and mu2. The mu1 is equal to 2 mu0 over 5 mu2 for mu2, 5 mu0. And then the B2T as shown there, 10 R component minus 20Z. So proceed to the end, you can find the B1 tangential component will equal to 4 R component minus 8 Z component milli-Tesla. Yes, so this is our B1T, and we do have already our B1 as shown here. So just combine them to find the complete set of B1 vector. The B1 vector finally is equal to 4R component plus 15 phi component minus 8 Z component, unit of milli-Tesla. Okay, guys, so that's the first step, right, to find the B1 vector. Now we are going to calculate the energy density in each region, right, in two media. So alright, so let's proceed to the next part. So I'm going to find the energy density. So the energy in this case, you can use these equations. The magnetic energy WH or WM is equal to half integrations mu h square dV. Okay, guys, so now since we are going to find the magnetic density, so you can simply put the volume part down there. So now we have here magnetic energy over volume, which is equal to magnetic density, is equal to the half h squared. Okay, guys, so the h here, guys, can be obtained from our previous result. If you want to find the magnetic density for the first region, let's say I want to find the magnetic energy for first region, so just use the H1 here. Right, same thing goes if I want to find the magnetic energy for second regions. So just use the H number 2 squared. Alright, guys, so now let's proceed. We have already our B1 is equal to 4R component plus 50 phi component minus 8Z component in millitesla. So we can simply find our H1 vector by dividing the B1 over its mu. So we can have here the 4R component plus 15 phi component minus 8Z component over, and actually the mu1 here is equal to, so here we have mu1, here we have mu2. mu1 is equal to the 2 mu naught. Okay guys, so that's our H1. So let's put the value of H1 squared over there. So guys, at this case actually we are looking for the magnitude of the vector of H1. So just simply put inside the value. So now we're going to find the magnetic energy for first region. So here you have mu naught 2 for your mu1 over 2, and now we're going to have here the 4R component plus 15 phi component minus 8Z component. Now we have all here have milli unit, and then over its mu 1 is equal to mu 2 mu naught. Okay guys, so all these things guys we have to square. Okay, and then take the magnitude of the H. Right, so again here gonna have here mu naught, and they just 4 milli squared plus 15 milli squared plus minus 8 milli squared, and then we have square root to take the magnitude, right? And then over here 2 mu naught. Okay, lastly have to square all of them. So now we are going to have this one, the mu naught over 4 mu naught squared, right? So you can have this one 4 milli squared plus 15 milli squared plus minus 8 milli squared, and then because this 2 and square is gone, so guys, when you can have here magnetic energy for first regions, magnetic energy density, you have this value finally, which equal to 60.678 joule per meter cube. Okay guys, so this is the answer for the first region. So if you repeat the same process, the same step to find the magnetic energy density for the second region or second media, you will find the value of it, which equal to the magnetic energy density for the second media. You have here the value of 57.7 joule per meter cube. Right guys, so I hope you can try yourself and make sure you really understand the flow or the concept of these problems. So I hope you can try, and all the best for your study. Okay.